So far with limits, we've talked about how to figure them out using an XY table and using a graph. The next step is to do what's called evaluating them analytically. And what that means, if I say I want to do something analytically, or sometimes we also say algebraically, that means using the equation itself, not the graph at all, or a table. Now, if you're going to do limits analytically or algebraically, the first thing you always want to try is direct substitution. And what that means is whatever x is approaching, if you're doing the limit as x approaches 10, before you do anything else, just plug 10 in for x and see what happens. And I'm going to show you an example of what could happen and then explain to you why it would or wouldn't happen. So let's say I asked you to do the limit as x approaches 5 of 2x squared minus 3x plus 1 all over x plus 1. And we're not going to graph it like we did in part 2. We're not going to make an XY table like we did in part 1. We're going to try to do it just from what we see here. So what I just finished telling you guys, the first step, no matter what, just take that 5, because x is approaching 5, and just plug it in and see what happens. So if I plugged it in, I have 2 times 5 squared minus 3 times 5 plus 1 all over 5 plus 1. Now what happens is you come out with an answer. The top comes out to 36, the bottom comes out to 6, and 36 over 6 just equals 6. Now that's the answer to the question. You're done. What's happening here, if you remember from our part 2 notes from the last section, I said the easiest type of limit is the continuous function that just crosses right over the line. That's the visual of what happened here. Let me show you guys what we're looking at. So let's say I'm doing this limit question. I'm doing the limit as x approaches 5. Now, when I plugged in 5 and I got the answer of 6, that means up here at this point, 5, 6, basically it was a continuous graph that just crossed right through it. I don't know what the rest of it looks like, but basically you have this graph that just crossed right through it like that, and that's the answer to the question. So by doing direct substitution, you're checking to see if this is one of those really easy limits where it's basically just the function value, f of x. So I plug in 5, I got 6, that's the answer, I'm done. Now the problem is, when you try direct substitution, sometimes it doesn't work. So if you try direct substitution, and instead of getting 6 for an answer, you get what we used to call undefined, or DNE, does not exist, that's when you know you have to try something else. And I said in the notes, usually that happens from getting a 0 in the denominator. So here are some of the things that direct substitution can give you. Number 1, direct substitution can give you a constant. I called it C for the notes. That's the answer to the question. So that was our first example. If I asked you to do the limit as x approaches 5 of something, and you plug in 5, and you clean it up and the answer is 6, you're done with the question. That's the answer. That's the easy one. Now, there are 2 other things that can happen. You can get a constant over 0, like 5 over 0 or negative 7 over 0. It doesn't matter what the number is. Any number over 0 represents a vertical asymptote, and it means the limit does not exist. Now here's the tricky one. If you get 0 over 0, so not a constant, not 5 over 0, but 0 over 0, what that means is you have that graph like we saw in part 2 of the last section, where there's a hole in the graph, and the function itself is undefined, but there is a limit and you can find it. So that's why I said more work needed. So let's look at this example here. So I have the limit as x approaches negative 2 of x minus 1 over x plus 2. And what I told you guys is, before you think about anything else, number 1, always direct substitution. So let's plug in negative 2 for those x's. So if I do that, I'm basically going to have negative 2 minus 1 over negative 2 plus 2. Now on top, negative 2 minus 1 is negative 3, and on bottom, negative 2 plus 2 is 0. So we got the constant over 0. What that means, what I'm thinking to myself, visually, is I found a vertical asymptote. critical asymptote. But that's not the answer to the question. The answer to the question about the limit itself is does not exist. So for now, any constant over 0, you can automatically just say does not exist. So let's take a look at this example here. And we're going to do direct substitution again. This is another limit question. Limit as x approaches 1 of a longer function. But let's do the same thing. Let's do direct substitution. So I'm going to plug in 1 for all of those x's. I would have 1 cubed minus 1 squared plus 1 minus 1. And on the bottom, I would have 1 minus 1. So what you end up with is positive 1 minus 1, positive 1 minus 1. That does equal 0 on top. And on bottom, 1 minus 1 is also 0. So we got the 0 over 0, which means there's a hole in the graph. And that also means we don't know what the answer is yet. There's a hole in the graph, but we don't know where it is. So what I'm going to do, I'm going to pause on this question. We're going to do some more notes on what to do when there's a hole, and then we'll come back and finish this question. So to determine the answer for the limit when you do get a 0 over 0, or when you figure out that there's a hole in the graph, there's a few things you can do. Number one, and I want to, even though it's not what we're doing today, I want to mention what you could do is what we did in section 3.2. So you can use either of the things we've learned so far. You can use a graph and look for where that hole is. You can make an XY table and look for patterns with the numbers. Or let's say we can't. Let's say for whatever reason we don't have the graph, we're not allowed to use a graphing calculator or Desmos or anything like that. We have to do it analytically. Here's some tricks you can do. I always call it fixing it. We need to fix this thing so that the 0 over 0 disappears and the answer is left over. Now there's a few tricks we're going to focus on for fixing it. Number one is factoring. That's what we practiced in chapter 2. Number 2 is rationalizing. You learned last year and I'll go over with you again. And then number 3, I know it's kind of hidden behind me, that says simplifying complex fractions. So I'm going to go over those 3 tricks for you. Now I am going to add on the notes here. There are more ways to do this. I put etc. Those are the 3 we're going to focus on because when we do derivatives next chapter, those are the 3 most common ones. Now before we go back to our example, here's a couple hints for you guys. The goal is to cancel out the thing that is causing that 0 over 0. And that might seem kind of weird. When we go back to our example, I'll show you exactly what I mean. But you always want to focus on what we're trying to cancel. Now, after you cancel out that 0 over 0 factor, you just start the problem over. You do direct substitution again, and it should work this time. So let's go back to our earlier example. This was the same example we just looked at. And we tried direct substitution. We already got the 0 over 0. I'll make a note of it. So we tried direct substitution. We got the 0 over 0. We're on step 2. So I think, all right, well, what I'm trying to, no, let me go back to that thing I said in the last slide too. You're trying to cancel out the factor that's causing the problem. Now the factor that's causing the problem is the x minus 1. See, every time I put x minus 1, every time I plug in 1, I get 1 minus 1, which is 0. So what that means is even though I don't see it right now, there's also an x minus 1 on top because I'm getting a 0 there too when I do direct substitution. So I think if I factor the top, then I can find that x minus 1, I can cancel it with the one on the bottom and get rid of the 0 over 0 and go from there. So I'm going to do this. I'm going to rewrite the question as limit as x approaches 1. I'm going to leave the x minus 1 on bottom, and then I'm going to factor the top. So this is just what we finished doing a whole chapter on, is factoring polynomials. So let me go off to the side. I'm going to do some synthetic division here. So if I take the polynomial from the top, I have 1x cubed, negative 1x squared, 1x, and negative 1. Now here's the thing. We already know what we're factoring out. In fact, what I'm going to end up with is x minus 1 times something. I know that because I need to cancel out the x minus 1. I know it's there. It has to be there. So if I want to divide out the x minus 1, what I'm going to put over here is positive 1. Remember, just synthetic division from last chapter. You change the sign on the factor for synthetic division. Okay, so let's do our synthetic division. I drop down the 1. 1 times 1 is 1. I add, I get 0. 1 times 0 is 0. Add, I get 1. 1 times 1 is 1. Add, I get 0 again. So I've gone from x cubed, where I started, to x squared. So this represents 1x squared plus 0x, I won't even put that in, plus 1. That's what goes inside the parentheses here. That's how synthetic division works. This 1 represents the x minus 1. This represents what's left over after I factored it. So those two things are what we factored into. So now I go back to the problem, and now I can do this. This is what I want to do the whole time. I said I want to get rid of these x minus 1s because whenever I plug in 1 for x, that's going to turn into a 0 over 0. Now, what I said before is once you've done that, once you've canceled out the trouble factor, just start the question over. So what I have left now is the limit as x approaches 1 of just x squared plus 1. You know, there's no denominator anymore. We canceled it. If you do direct substitution now, you should get the right answer. So I'm going to plug 1 in for the x that's left over. I get 1 squared plus 1, which is 1 plus 1, or 2. So my final answer to that question is 2. What we know about the graph, even though we're not graphing right now, just to tie in with last section, what we know about the graph is that there's a hole in this graph where x equals 1, and the height of that hole is 2. That's what we just found. So that's a good example of how you can do a limit analytically, it's called. I didn't need to see the graph. I didn't need an XY table. I figured it out just from the equation. Okay, so the second topic I wanted to talk to you guys about, if you remember from a few slides back, I said another common way to do this besides factoring is by rationalizing. And I said I'll review it with you guys because we haven't done it together yet this year. I think you did it last year. But basically, to rationalize an irrational expression. So irrational pretty much means it's got a square root in it, some sort of square root. If you want to cancel out a square root or rationalize it, you multiply by conjugates, just like we did with imaginary numbers. And what happens is a lot of times by rationalizing this irrational expression, that term that you are trying to cancel out disappears. You cancel it out and then you can do direct substitution again. So let's do an example of that. We have the limit as x approaches 0 of x over the square root of x plus 1 minus 1. And let's do our direct substitution first. Always direct substitution first. So I'm going to plug in 0 for x. Remember, you're direct substituting this number here. So I get 0 over square root of 0 plus 1 minus 1. And that would be 0 over square root of 1 minus 1. Now the square root of 1 is 1, and 1 minus 1 is 0. So we do get the 0 over 0. This is the same setup as the last time. So I know there's a hole in the graph, which means I have to do a little bit of extra work. Let's get rid of all of this. So we have that work. We found the 0 over 0. Let's clear some space so we can do the question. All right, so here's the new part of this question. I said, well, actually, let me go back a half step. Once you realize you get the 0 over 0, my target for this one, the thing I want to cancel out is this x right here. Because if I'm plugging in 0 for x, that's the 0. So what that means is, again, even though I don't see it right now, there's a hidden x in the bottom. If I can find it and cancel it with that one on top, I can do direct substitution and find my answer. So let's see if we can find that x. And what I told you guys is a good trick here. Anytime you see a square root in your question, try rationalizing it. Now, because it's a fraction, I'm going to multiply top and bottom by the same thing. And what I'm going to multiply by is the conjugate, meaning the exact same thing, but with a plus instead of a minus in between the square root part and the number part. So I'm going to leave the square root part, square root of x plus 1, and instead of doing minus 1, I'm going to do plus 1. Now, because it's a fraction, I have to multiply top and bottom by the same thing. So let's see what we get here. We have the limit as x approaches 0 still. It's still a limit question. Now what I'm going to do, on the top, I'm just going to leave everything. Don't distribute the x. So remember, I circled it in green to make it stand out. My goal for this question is to cancel out the x. If you want to cancel it, leave it. If you distribute it into the parentheses, you can't cancel it anymore. So don't ever multiply, or distribute or FOIL out the thing you're trying to cancel. Leave it where you can cancel it. Now on the bottom, what you do is you multiply conjugates. Now the shortcut here, we just finished talking about this with imaginary numbers. When you multiply conjugates, the middle terms always cancel. That's what conjugates do. So I'm not even going to do the middle parts. I'm going to say when I multiply x plus 1 times x plus 1, it's actually square root. When I multiply a square root times itself, the square root cancels. So I get the square root of x plus 1 squared, which is basically just a regular x plus 1. Square root times square root gives me a regular number. Now the middle terms cancel. Like I said, I'm just going to skip that part. I would have plus square root of x plus 1 minus square root of x plus 1 and cancel them. And then I do negative 1 times 1, which is just negative 1. Now what happens on the bottom? The plus 1 and the minus 1 cancel. So what I get is, we'll leave the top again, just x on the bottom. And remember, that's what I wanted the whole time. I circled it in green up top. My goal this whole time was to cancel out x. Once the x's are gone, direct substitution should work with what's left over. Now what's left over here, I'll recopy it. Limit as x approaches 0 of just square root of x plus 1 plus 1. And now I'm going to plug in 0 for the x that's remaining. So for the last part of the question, if I do direct substitution, I get square root of 0 plus 1 plus 1. And that would be square root of 1 plus 1, 1 plus 1. That's going to be 2 again. We'll get the same answer as last time. So that's an example of how you can use rationalizing to cancel. But remember, both questions started the same way. It started with a 0 over 0. And then the second part was me looking here and picking out the thing that I want to cancel. I said every time I plug in 0, if I plug in 0 for x, I get a 0. The zeros are what's causing me a problem. So I said I need to find an x in the bottom that I can cancel with the top and then direct substitution with the rest of it. All right, I'll do one more example with you guys. This is a complex fraction one. So we have done a little bit of this together this year. A complex fraction is when you have a smaller fraction inside of a bigger fraction, like I have the 1 over x or the 1/2, and it's inside this bigger fraction. And let's see what we do with that. Sometimes just cleaning them up helps. So before I do anything, of course, I'm going to do direct substitution. Now this time I'm plugging in -2 for x. X is approaching -2. So if I do my direct substitution here, I would have 1 over -2 plus 1/2, and on the bottom I would have -2 plus 2. Now that's on top, -1/2 plus 1/2 is 0, and on bottom -2 plus 2 is 0. So I did get the 0 over 0 again. So for the third time in a row we got 0 over 0, which means there's a hole in the graph. And I'm going to show you the third way, the third common way of fixing that. So I'm going to erase our work again. Get some space here. All right, so this one, what I want to do is basically just fix those smaller fractions so we don't have a complex fraction anymore. And this is the part that I said we actually have done. There's a few ways to do it. To me, the easiest way is to always do this. Group the top and bottom, and then multiply top and bottom by whatever it takes to cancel out each one of the small denominators. So basically, I need to multiply by 2x. If I multiply everything by 2, it'll cancel that 2 and the 1/2. And if I multiply everything by x, it'll cancel the x in the denominator of the 1 over x. So if I multiply by 2x, it'll wipe out all the denominators. Let's do that and see what happens. Also, let me say this. I'm going to circle it in green again. The thing that I'm trying to cancel here, I think, is this x plus 2. Because I'm substituting -2, and every time I do that, I get -2 plus 2, which is 0. So if I can find a way to cancel out that x plus 2, that's what I want to do. All right, so what I have now is the limit as x approaches -2. Now on the top, I'm going to distribute. Now when I multiply, each one will cancel one thing. So like when I multiply here, I get 2x over x. Well, that's just 2. And on the second one, I get 2x over 2, put the plus in the middle, 2x over 2, which is just x. So basically, I just get 2 plus x on top. Now on the bottom, remember what I said in the last example, don't distribute the 2x. The x plus 2 is what we're trying to cancel. If you distribute the 2x, the x plus 2 disappears, you can't cancel it anymore. So once you've figured out the thing you're trying to cancel, don't mess with it, leave it alone. So I'm going to leave this, I'll put the 2x in front. I'm going to leave it as 2x times x plus 2. Now when you look at this question, what you realize, x plus 2 and 2 plus x are the same thing. When you're adding numbers, it doesn't matter what order they are. So those cancel. An x plus 2 and a 2 plus x cancel each other out. That's gone, that's gone. Now the one thing you want to be careful of here, if you cancel everything from a denominator, it basically just disappears. If you cancel everything from the top, you want to leave a 1 there. So what I have right now is the limit as x approaches -2, not just 2x, you have 1 over 2x. And now for our final answer, I'll do my direct substitution again. I'm plugging in -2, so I have 1 over 2 times -2. That would be 1 over -4, or I'll call it -1/4 for my answer. And that is the answer, that's the limit. So this is a little bit tougher than what we did with the graphs and what we did with the tables. It's a little bit more work. But if you have to, like if you don't have, if you're not allowed to use Desmos, you don't have a graphing calculator and you have to do a limit, this is the best way we have to do it right now. All right, so you guys get started on the homework and I will answer any questions you have in class tomorrow.